Some stars are observed once, catalogued, and left to the slow business of time. Others are different. There is a small group of stars in this galaxy that have earned the permanent attention of observatories, satellites, and research teams that return to them year after year, decade after decade. These are stars that behave in ways science is still working to explain. We are going to look at them carefully, one by one, and consider what it is about them that makes astronomers unwilling to look away. You're listening to Sleepy Time Universe, calm science for curious minds seeking rest. We will move through each of these stars one by one and consider what the watching has revealed. If this sounds like the kind of content you return to, consider subscribing and leaving a comment below. We would love to know, which of these stars do you find most remarkable? Now let's begin. Chapter 1. What it means to watch a star. Watching a star is not a simple thing. It is not a matter of pointing a telescope at the sky on a clear night and noting what is there. When astronomers speak of monitoring a star closely, they mean something far more sustained and deliberate than that. They mean years of repeated observation across multiple wavelengths of light. They mean satellites positioned to catch signals that never reach the ground. They mean research teams whose entire careers are built around a single object, returning to it with each new instrument and each new question that science finds the tools to ask. The night sky, as most of us experience it, feels permanent. The stars appear in the same positions, hold the same brightness, follow the same paths across the seasons. That appearance of permanence is one of the things that makes the sky restful to look at. But it is an illusion produced by the vast distances involved and the shortness of a human life. Stars are not still. They are not fixed. They are enormous engines running through fuel at rates that would be difficult to hold in the mind, and many of them are changing in ways that only become visible when you watch them carefully over long periods of time. The stars that have earned sustained, dedicated monitoring are the ones where that change is happening on timescales short enough for science to observe directly. Not the slow drift of a main sequence star burning steadily through hydrogen over billions of years, but something more immediate. A star that dims unexpectedly and then recovers. A binary system that erupts on a cycle measured in years rather than millennia. A remnant so magnetically extreme that it periodically sends energy across tens of thousands of light years and leaves a measurable trace on instruments here on Earth. These are the objects that have moved from the catalogue into the realm of active study, and they tend to stay there. There is also something worth understanding about what watching a star actually requires. Ground-based observatories can capture visible light and some radio frequencies, but the universe operates across a much broader range of the electromagnetic spectrum. X-rays and gamma rays are absorbed by the atmosphere before they reach the ground, which means that some of the most important signals these stars produce are invisible to any telescope built on the surface of the Earth. Observing them requires instruments in orbit. NASA's Chandra X-ray Observatory, the New Star Telescope, the Fermi Gamma Ray Space Telescope, and the Hubble Space Telescope have all contributed to the long-term study of the stars we are going to explore. Each one was built to capture a different kind of light, and together they allow astronomers to build a picture of these objects that no single instrument could provide alone. This layering of observation across different wavelengths is part of what makes modern stellar astronomy so different from what it was a century ago. In the 19th century, astronomers could only work with visible light. They could measure brightness, track position, and analyze the spectrum of a star to determine its composition and temperature. That was already a remarkable body of knowledge. but it left entire categories of stellar behavior completely hidden. The most energetic events in the universe, the eruptions, the magnetic outbursts, the collisions of stellar winds at speeds of millions of miles per hour, produce radiation that visible light astronomy cannot see. The satellites and space telescopes launched over the past several decades have opened those hidden channels, and many of the most closely watched stars in the galaxy owe their current status to something that was only discovered once the right instrument was finally in orbit. There is a patience to this work that is worth acknowledging before we move into the stars themselves. Monitoring campaigns for objects like Eta Carinae have been running for more than 2 decades without interruption. The researchers involved have watched the same system through multiple orbital cycles, building a model one observation at a time. That kind of sustained attention is rare in science, where funding cycles and changing priorities tend to pull researchers toward new objects and new questions. The fact that certain stars have held the field's attention for so long is itself a signal. It means that what is being found there is consistently interesting enough to justify the continued investment, and in each case, that judgment has proven correct. We will look now at the stars themselves, beginning with the one that most people on Earth can find on any clear winter night, and which gave the entire astronomical community reason to pay very close attention indeed. Chapter 2. Betelgeuse, the star that never stops changing. Betelgeuse is one of the most familiar stars in the night sky. It marks the right shoulder of Orion, and on a clear winter night in the northern hemisphere, it is easy to find. A distinctly reddish point of light sitting above and to the left of the 3 stars that form Orion's belt. It has been known and named across many cultures for as long as people have been paying attention to the sky. But familiarity, in this case, has not produced complacency. Betelgeuse is one of the most studied stars in the galaxy, and the reasons for that attention have only grown stronger over time. It is a red supergiant, which means it has passed through the main phase of its life and expanded to a size that is genuinely difficult to hold in the mind. If Betelgeuse were placed at the center of our solar system, its outer atmosphere would extend somewhere beyond the orbit of Jupiter. The precise measurement has been revised several times as observing techniques have improved, but in all estimates, the scale is the same. This is an object so large that the distance from the Sun to Jupiter, which takes light more than 40 minutes to cross, would fit comfortably inside it. Our Sun, by comparison, is a small and unremarkable thing set against a star of this kind. Betelgeuse is not the most massive star we will discuss in this video, but it is among the most evolved. Red supergiants expand as they age, and that expansion comes at the cost of density. Betelgeuse has somewhere between 10 and 20 times the mass of our Sun, but it has spread that mass across a volume so enormous that its average density is far lower than the Sun's. The outer layers of Betelgeuse are thin enough to be considered a very good vacuum by laboratory standards on Earth. What makes it extreme is not density, but scale, and the stage of life it has reached. That stage is late. Betelgeuse has already passed through the hydrogen-burning phase of its life and moved into later stages of nuclear fusion, building progressively heavier elements in its core. At some point, it will exhaust the last fuel available to it. Its core will collapse, and the result will be a supernova, one of the most energetic events the universe produces. When that happens, Betelgeuse will briefly become visible in the daytime sky from Earth. It is close enough, roughly 700 light-years away, that the explosion will outshine everything in the night sky except the moon. It will cast shadows at night. The constellation of Orion as we know it will be permanently changed. The question that cannot be answered with certainty is when. Betelgeuse could go supernova at any point within the next 100,000 years, and the uncertainty in that range is genuine rather than a failure of scientific imagination. What the models have established is that the star is close to the end of its life in astronomical terms, and that the signs of that proximity are visible in its behavior. That behavior is variable in ways that have been observed and recorded for well over a century. Betelgeuse does not shine with a constant brightness. It pulses, brightening and dimming on cycles that astronomers have identified and studied in detail. The most prominent of these cycles runs roughly 420 days, driven by physical pulsations in the star's outer layers, expansions and contractions that alter both its size and the amount of light it releases. There is a longer cycle of several years layered beneath that, and shorter, irregular variations above it. The result is a star that is always shifting, always doing something that a careful observer can detect and record. Long-term brightness records for Betelgeuse stretch back to the late 19th century, giving astronomers a baseline against which to measure anything unusual. And in late 2019, something unusual happened. Beginning in October of that year, Betelgeuse started to dim. This was not alarming in itself. The star dims regularly as part of its pulsation cycle. But this dimming continued past the point where the cycle would normally reverse. By February of 2020, Betelgeuse had reached a brightness roughly 40% below its typical level, making it noticeably fainter than observers were accustomed to seeing. It had dropped out of the list of the 20 brightest stars in the night sky, which it normally occupies comfortably. The change was visible to the naked eye, and it was visible to every telescope trained on it. The astronomical community responded immediately. The event became known as the Great Dimming, and it prompted a surge of observing activity from facilities around the world. Proposals were submitted, observing time was requested, and data began accumulating from instruments operating across every available wavelength. The question of what was happening to Betelgeuse became one of the most discussed topics in stellar astronomy, and the range of proposed explanations reflected genuine scientific uncertainty. The first explanation many researchers reached for was the one that had been quietly anticipated for years. If Betelgeuse was dimming more dramatically than its normal cycle could account for, perhaps this was the beginning of the end, the first visible signal of a star entering its final phase before collapse. This possibility was taken seriously enough to appear in scientific discussions almost immediately, and it found its way into public conversation with considerable speed. It was not, as the data gradually revealed, what was happening. The picture that assembled itself from the accumulated observations pointed toward two overlapping processes. The first was a particularly deep trough in one of Betelgeuse's regular pulsation cycles, which had brought the star to a phase of reduced brightness at the same moment the second process was occurring. That second process involved a large mass ejection from the star's surface, an outflow of material that cooled as it moved away from the star and condensed into dust. Dust absorbs and scatters light. A cloud of newly formed dust sitting between Betelgeuse and Earth would reduce the brightness reaching our instruments, and it would do so in a way that looked, from a distance, like the star itself had grown darker. The Hubble Space Telescope observed the ultraviolet emission from Betelgeuse during the event, and found evidence of a dense, hot plume of material that had risen from the star's surface. A surface mass ejection on a scale far larger than anything the Sun produces. As this material moved outward and cooled, it formed the dust cloud responsible for a significant portion of the dimming. The combination of the pulsation trough and the dust obscuration produced the dramatic brightness drop that had drawn the world's attention. Betelgeuse was not about to explode. It had shed a piece of itself. That material had become dust, and the dust had briefly dimmed it. What the episode left behind was a set of questions that have kept the monitoring programs running at full intensity ever since. The mass ejection was not something stellar models had predicted at that scale, and the mechanism driving ejections of that magnitude is not fully understood. In the period following the Great Dimming, Betelgeuse's pulsation cycle appeared to shift slightly, as though the ejection event had disrupted rhythms that had been recorded for over a century. The 420-day cycle seemed to shorten somewhat, and researchers found themselves working to understand whether this represented a temporary disruption or a more lasting change in the star's internal dynamics. The James Webb Space Telescope has since contributed observations of Betelgeuse that were not possible with earlier instruments. Its infrared sensitivity allows it to study the dust and gas surrounding the star in detail that previous telescopes could not achieve, and the material ejected during the Great Dimming can now be traced outward from the star and studied as it disperses. That dispersal carries information about the composition and behavior of the star's outer layers that feeds back into the models of how red supergiants age and what the period immediately before a supernova actually looks like from the outside. Betelgeuse has been known to humanity for thousands of years. For most of that time, it was simply a red star in a familiar constellation, notable for its color, but otherwise unremarkable in terms of what could be learned from it. The tools that have allowed science to understand what it actually is: a red supergiant in the late stages of its life, a star capable of ejecting mass on a scale that dims it to the naked eye, an object whose interior is building toward one of the universe's most energetic events, are almost entirely modern. The star has not changed. What has changed is our ability to ask it questions and to understand what it tells us in return. Chapter 3. Eta Carinae, the star that shouldn't still exist. There is a star system in the southern sky that has been described, without exaggeration, as the most violent stellar environment within 10,000 light-years of Earth. It is not visible from most of the northern hemisphere, and it does not appear in the familiar constellation maps that many people grow up with. But among astronomers who study massive stars, Eta Carinae occupies a category of its own. It is an object that has behaved in ways that surprise the scientists watching it, that continues to behave in ways that are not fully explained, and that has been under more or less continuous observation since the middle of the 19th century, making it one of the longest-running subjects of stellar monitoring in the history of astronomy. Eta Carinae is not a single star. It is a binary system, two massive stars in an eccentric orbit that brings them unusually close to one another every 5.5 years. The primary star is one of the most luminous objects in the galaxy. It has a mass somewhere around 90 times that of our Sun, and it outshines the Sun by roughly 5 million times. The secondary star is smaller, but still enormous by any ordinary standard, with a mass estimated at around 30 times that of our Sun, and a luminosity of approximately 1 million times solar. These are not stars that sit quietly. Both of them drive powerful outflows of gas called stellar winds, moving at speeds that reach several million miles per hour, and where those winds collide, the environment becomes one of the most energetically extreme places in the known galaxy. The orbital period of 5.5 years means that the two stars spend most of their time at a considerable distance from one another, then swing close in an approach that dramatically intensifies the interaction between their winds. At closest approach, the stars are separated by a distance roughly equivalent to the average gap between Mars and the Sun, which sounds large in human terms, but is extraordinarily intimate for two objects of this mass and luminosity. The collision zone between their winds at that point generates temperatures that reach tens of millions of degrees, producing X-ray emission that has been tracked across multiple orbital cycles by NASA's Chandra X-ray Observatory. That periodic X-ray signal has become one of the primary tools for studying the system, and the variations in it as the stars approach and recede have allowed researchers to build increasingly detailed models of how the two winds interact. What draws astronomers to Eta Carinae most intensely, however, is not its current behavior, but its recent history. In the 1840s, the system underwent an eruption of extraordinary scale. For reasons that are still not fully understood, Eta Carinae brightened dramatically over a period of years, eventually becoming the second brightest star in the night sky in 1843, outshone only by Sirius. This event, which astronomers now call the Great Eruption, was visible to observers across the southern hemisphere who had no framework to explain what they were seeing. The star then faded over the following decade, dropping below naked eye visibility entirely by the 1850s. What the Great Eruption left behind is still visible today. The energy released during those years ejected an enormous quantity of material from the system, enough mass to make several copies of our Sun, and that material formed the structure now known as the Homunculus Nebula. The homunculus is a pair of lobes of gas and dust expanding outward from Eta Carinae at speeds of around 1.5 million miles per hour. It is now roughly a light year across, and it is one of the most photographed objects in stellar astronomy. Images from the Hubble Space Telescope show it in extraordinary detail. Two billowing clouds of orange and red surrounding the brilliant central point of the binary system itself. The cause of the Great Eruption remains one of the open questions in stellar astrophysics. A true supernova releases energy by destroying the star that produces it. Eta Carinae released an amount of energy during the 1840s that approached supernova levels, but the star survived. It did not explode. It shed an enormous portion of its outer mass, produced a nebula visible across thousands of light years, and then continued on. This kind of event, sometimes called a supernova imposter, is not well understood theoretically, and Eta Carinae is the closest and best studied example of a star that has produced one. Understanding what caused it and whether it can happen again is one of the central motivations for the monitoring programs that have been running ever since. The system also produced a smaller eruption in 1890, which caused it to briefly brighten again before fading once more. This second event added another layer of complexity to the picture. Two major outbursts within 50 years from a system that should theoretically be approaching the conditions that precede a supernova raised questions about the stability of massive stars that have not been fully resolved. Eta Carinae is thought to be close to or beyond what is called the Eddington limit, the point at which a star's outward radiation pressure exceeds the gravitational force holding it together. A star in that condition is inherently unstable, and the history of Eta Carinae is consistent with that instability expressing itself in repeated, violent outbursts. Since the development of space-based astronomy, the tools available for studying Eta Carinae have expanded considerably. The New Star Telescope discovered that the system is accelerating particles to near the speed of light, producing high-energy X-rays that suggest Eta Carinae is a source of cosmic rays. charged particles that travel across interstellar space and occasionally reach Earth. The Fermi Gamma-Ray Space Telescope has detected gamma-ray emission from the system that varies with the orbital period of the binary, adding another wavelength of confirmation to the model of wind collision as the primary energy source. Hubble has tracked the Homunculus Nebula across decades of observation, watching it expand and revealing fine structures within it that carry information about the sequence of events during the Great Eruption. What has emerged from all of this watching is a portrait of a system that is genuinely extreme in multiple directions at once. It is massive enough to be near the theoretical upper limit for stellar mass. It is luminous enough that its radiation pressure works against its own gravity. It has a history of eruptions that no current model fully explains, and it sits close enough to Earth, in astronomical terms, that the instruments we have built can study it in real detail, rather than observing it as a point of light too distant to resolve. There is a particular quality to the way Eta Carinae is discussed in the scientific literature that is worth noting. Researchers who have spent careers studying it tend to describe it with a kind of careful restraint, as though the system has a history of surprising people and they have learned not to assume they know what it will do next. The monitoring continues, not because the answers have run out, but because the questions keep deepening. Each new observation adds detail to a picture that is already extraordinarily complex, and the picture is still not complete. Chapter 4. UY Scuti. The question of size. There is a question that comes up reliably whenever people begin exploring the scale of stars, and it is a question that turns out to be considerably more complicated than it first appears. The question is simply this: what is the largest star in the universe? It sounds like the kind of thing that should have a clean answer, a name, a catalogue number, a set of measurements that settle the matter. But the reality of how astronomers measure stellar size and the genuine difficulties involved in making those measurements accurately means that the answer has shifted more than once and continues to be debated. UY Scuti has held a place near the top of that list for some time. It is a red supergiant located in the constellation Scutum, roughly 5,000 light-years from Earth, and for a period it was widely cited as the largest known star by radius. The numbers associated with it are striking. Its radius has been estimated at somewhere around 1,700 times that of the Sun, though more recent measurements have placed it somewhat lower, closer to 1,100 to 1,200 solar radii depending on the method used. Even at the more conservative end of that range, the scale is genuinely difficult to hold in the mind. To get some purchase on what these numbers mean, it helps to think about what it would take to travel around a star of this size. Light, moving at the fastest speed the universe permits, would take several hours to travel around the circumference of UY Scuti. A commercial aircraft traveling at its normal cruising speed, following a path around the star's equator, would require well over 1,000 years to complete a single circuit. These are not figures that become more comprehensible the longer you sit with them. They simply register as very large, and then remain there at the edge of what the imagination can usefully do with numbers. UY Scuti is a pulsating variable star, which means its size is not constant. Like Betelgeuse, it expands and contracts on a cycle driven by processes in its interior, and the brightness variations that result from this pulsation have been observed and recorded since the 19th century. The star was first catalogued by German astronomers at the Bonn Observatory in 1860, making it one of the earlier entries in the long record of variable star observation. What those early observers could not have known was the scale of what they were looking at. the instruments and techniques needed to measure stellar radii with any precision would not exist for many decades. The difficulty in measuring the size of a star like UY Scuti illustrates something important about how stellar astronomy works. Stars are so distant that even the largest of them appear as points of light in most telescopes. Measuring the actual angular diameter of a star, the tiny angle it subtends against the sky, requires either very long baseline interferometry, which combines signals from multiple telescopes to achieve very high resolution, or indirect methods that infer size from brightness, temperature, and distance. Both approaches carry uncertainties, and those uncertainties compound when the star in question is embedded in a region of dust and gas that affects how its light reaches us. UY Scuti sits within a region of the Milky Way, where interstellar dust is present in significant quantities, and that dust absorbs and reddens the star's light in ways that must be corrected for when calculating its properties. The correction introduces uncertainty into the temperature estimate, and since size is calculated in part from temperature and luminosity, that uncertainty propagates through to the final radius measurement. This is why the numbers associated with UY Scuti have been revised over time, and why different studies have produced figures that vary by several hundred solar radii. It is not a failure of measurement so much as an honest reflection of how hard this particular measurement is to make. What is not in doubt is that UY Scuti belongs to a class of stars, the red supergiants, that represent one of the final stages in the life of a massive star. Like Betelgeuse, it has moved off the main sequence, exhausted its core hydrogen, and expanded to many times its original size as it processes heavier elements. Also like Betelgeuse, it is variable in a way that reflects the dynamism of its interior, and its long-term behavior has been tracked across more than a century of observation. The variability cycle of UY Scuti runs on a period of roughly 740 days, longer than Betelgeuse's primary cycle, and the amplitude of its brightness variations is substantial enough to be detected with modest equipment. The reason UY Scuti continues to attract scientific attention goes beyond its size record. Red supergiants of this scale are rare, and each one that can be studied in detail adds to the understanding of how massive stars behave in their late stages. The processes that drive mass loss in these objects, the steady outflow of material from the star's surface driven by radiation pressure and pulsation, are important for understanding how the chemical composition of the galaxy changes over time. When a red supergiant eventually ends its life in a supernova, the material it has shed over thousands of years is already distributed through the surrounding space, enriched with the heavy elements the star has been producing. That material becomes part of the interstellar medium, available eventually to be incorporated into new stars and planetary systems. There is also a practical reason why the largest stars attract sustained observation beyond their scientific interest. They are among the brightest objects in the galaxy, which means they can be detected at distances where most stars would be invisible. Studying them in the Milky Way gives astronomers tools and calibrations that can then be applied to stars observed in other galaxies, where individual stellar properties are much harder to measure directly. UY Scuti and stars like it serve as anchor points in the broader project of understanding how galaxies work and how the stellar populations within them evolve over cosmic time. Whether UY Scuti is currently the largest star in the galaxy by radius is a question that may not have a definitive answer for some time. New measurements, new surveys, and new candidates continue to emerge, and the list of contenders at the top end of the size distribution shifts as techniques improve. What can be said with confidence is that it represents something genuinely at the outer edge of what stars are physically able to become. An object so expanded that the distinction between its surface and the surrounding space becomes difficult to define clearly. For a star that most people have never heard of, it occupies a remarkable position in the catalogue of the universe's most extreme objects. Chapter 5. R 136A1, the most massive star known. If UY Scuti represents the outer edge of what stars can become in terms of physical size, then R 136A1 represents something different and in some ways more fundamental. It is not the largest star by radius. It is the most massive, the star that sits closest to the theoretical upper limit of how much matter a single stellar object can accumulate and hold together. And the story of how it was discovered and what has been learned about it since touches on some of the deepest questions in stellar physics. R 136A1 is located in the Tarantula Nebula, a vast region of star formation in the Large Magellanic Cloud, a satellite galaxy of the Milky Way situated roughly 160,000 light-years from Earth. The Tarantula Nebula is one of the most active star-forming regions in the local group of galaxies, producing stars at a rate and scale that has no equivalent in the Milky Way itself. At its center sits a dense cluster of young, hot, massive stars known as R 136, and within that cluster, R 136A1 was identified as something exceptional. The mass estimates for R 136A1 have been revised upward more than once since the star was first studied in detail. Current estimates place its mass at somewhere between 150 and 250 times that of our Sun, depending on the model and the method used. Even the lower end of that range places it well beyond what stellar theory had long considered the upper mass limit for stars. For much of the 20th century, a figure of around 150 solar masses was treated as an approximate ceiling, the point beyond which radiation pressure from the star's own luminosity would prevent further mass accumulation during formation and drive the outer layers away. R 136A1 appears to sit above that ceiling, and understanding how it got there is one of the questions its study has raised. One possibility that researchers have explored is that R 136A1 formed through the merger of several massive stars that were originally separate objects. In the dense environment of a young star cluster, close gravitational encounters and physical collisions between stars are more likely than in the wider galaxy. A series of mergers early in the cluster's history could have produced a single object with a mass that no individual star could have accumulated through normal formation processes. This hypothesis is difficult to confirm directly, but it is consistent with what is known about the environment in which R 136A1 exists, and with the theoretical difficulties of forming a star of this mass through conventional accretion alone. What is observable is the star's luminosity, and the numbers there are extraordinary. R 136A1 outshines our Sun by somewhere between 4 and 8 million times, making it one of the most luminous stellar objects known in the universe. That luminosity is not produced by any exotic process. It is the straightforward result of nuclear fusion proceeding at a rate proportional to the star's enormous mass. More massive stars burn hotter and faster, and R 136A1 burns at a rate that will exhaust its fuel in a fraction of the time available to a star like the Sun. Its lifetime on the main sequence is measured in millions of years rather than billions, and it is already well into that brief period. The stellar wind produced by R 136A1 is correspondingly extreme. The radiation pressure from an object this luminous drives a continuous outflow of material from its surface at speeds of several thousand kilometers per second, and the mass loss rate is enormous by stellar standards. R 13601 is shedding the equivalent of the Sun's entire mass every few 100,000 years, a rate that means the star's current mass is already significantly lower than it was when it formed. The mass estimates that researchers work with today represent the star as it is now, not as it was at the beginning of its life, and accounting for the mass it has already lost is one of the complexities involved in reconstructing its history. Studying R 13601 in detail requires dealing with the challenges that come with its location and environment. At a distance of 160,000 light-years, individual stars in the Tarantula Nebula are not easy to resolve from one another. The core of R136 is extraordinarily dense, with many massive stars packed into a small volume, and separating the light of R13601 from its neighbors requires the highest resolution instruments available. The Hubble Space Telescope has been the primary tool for this work, and the images it has produced of the R136 cluster show a concentration of brilliance at its center that is difficult to convey in ordinary language. More recently, the James Webb Space Telescope has contributed infrared observations that penetrate the dust surrounding the cluster and reveal details of its stellar population that were not accessible before. What makes R136A1 particularly valuable to stellar science is precisely its extremity. A star at the upper mass limit, or beyond it, tests the models of stellar structure and evolution in ways that more ordinary stars cannot. The processes that govern how a star of this mass maintains itself against its own radiation pressure, how it loses mass over time, and what it will eventually become are not well constrained by theory alone. R136A1 provides an observable case study for those processes, and each new observation that adds detail to its portrait also adds constraint to the models. The eventual fate of R136A1 is a matter of active research and some uncertainty. A star of this mass, ending its life in a collapse, may produce a supernova of exceptional energy, possibly what astronomers call a hypernova. A collapse event orders of magnitude more energetic than a standard core collapse supernova. It may also produce a gamma-ray burst, one of the most energetic phenomena in the observable universe, if the geometry of the collapse is favorable. Or it may, under some conditions, collapse directly into a black hole without producing a visible explosion at all. The models that describe which of these outcomes applies to a star of R136A1's mass are still being refined, and the answer may depend on details of the star's internal structure and rotation that are not yet fully known. What is certain is that R136A1 will not burn quietly into old age. A star that lives fast and burns at this rate is not built for a gentle ending. Whatever it eventually becomes, the event will be worth watching, and the astronomers who study it are already building the tools they will need when the time comes. Chapter 6. Wolf-Rayet stars, burning at both ends. There is a category of star that represents something like the most extreme version of the process we have been describing throughout this video. Not the largest by radius, not the most massive by the numbers, but the most thoroughly committed to consuming itself. Wolf-Rayet stars are massive stars that have stripped away their own outer layers through the sheer force of their radiation, exposing the hot, dense interior regions that in a more restrained star would remain hidden for the entirety of its life. They are among the hottest, most luminous, and most short-lived stars known, and they have been the subject of sustained scientific attention since they were first identified in the second half of the 19th century. The category takes its name from the two French astronomers who first described it. In 1867, Charles Wolf and Wolf-Rayet, working at the Paris Observatory, noticed that 3 stars in the constellation Cygnus showed an unusual spectral signature: broad, bright emission lines where most stars show absorption lines. This was not a subtle difference. The spectra of these stars looked fundamentally unlike anything that had been catalogued before, and the feature has remained the defining observational characteristic of Wolf-Rayet stars ever since. The broad emission lines are produced by the star's powerful stellar wind, the continuous outflow of material from its surface moving at speeds of thousands of kilometers per second. And they carry information about the composition and velocity of that wind that can be read directly from the spectrum. What those spectra reveal is a stellar surface that bears no resemblance to the surface of the Sun. A typical main sequence star like the Sun presents a photosphere rich in hydrogen, the fuel that powers its nuclear reactions. Wolf-Rayet stars have lost most or all of their hydrogen envelope, exposing layers beneath that are dominated by helium, carbon, oxygen, or nitrogen, depending on the evolutionary stage the star has reached. This exposed interior is extraordinarily hot. Surface temperatures for Wolf-Rayet stars range from around 25,000 to over 200,000 degrees Kelvin, compared to roughly 5,800 degrees for the Sun. The hottest known star, WR102, is a Wolf-Rayet object, and its surface temperature has been measured at more than 200,000 degrees, a figure that places it in a different thermal category from almost everything else in the galaxy. The mechanism that produces this exposed interior is the stellar wind itself. Wolf-Rayet stars are losing mass at rates that are extraordinary, even by the standards of massive stars. The most active among them shed the equivalent of the Sun's entire mass every 10,000 years or so, continuously blasting their outer layers into the surrounding space. Over the lifetime of the star, this process removes the hydrogen envelope entirely and, in the most evolved objects, begins to erode the helium layer beneath it as well. What remains is a star that is essentially burning from the inside out. The nuclear reactions occurring in its interior are visible directly because the layers that would normally cover them have been blown away. This mass loss has consequences that extend well beyond the star itself. The material ejected by a Wolf-Rayet star's wind moves outward at high speed and collides with the slower moving gas that was shed earlier in the star's life, creating a shell of compressed material around the star that glows in a distinctive way. These structures, called Wolf-Rayet nebulae, are visible around many of these stars and have been studied as laboratories for understanding how stellar winds interact with the interstellar medium. They are also rich in the heavy elements that the star has been producing in its interior and then ejecting, making them important contributors to the chemical enrichment of the galaxy. The lifetimes of Wolf-Rayet stars are brief, even by the standards of massive stars. The most massive examples may spend only a few 100,000 years in the Wolf-Rayet phase before exhausting their remaining fuel and collapsing. WR102, the hottest known example, has been estimated to have a remaining lifetime of less than 2,000 years before it goes supernova, a figure so short in astronomical terms that it amounts to saying the event could happen essentially at any point on a cosmic timescale. The fact that we happen to be observing it during this final phase of its existence is a matter of chance, and the observation carries a particular quality because of it. Wolf-Rayet stars are also considered among the most likely progenitors of long gamma-ray bursts, the most energetic explosions in the universe. When a massive star collapses, the outcome depends heavily on how much angular momentum the core has retained and what happens to the material falling inward. In a Wolf-Rayet star that has shed its hydrogen envelope, the conditions may be right for the collapsing core to form a rapidly rotating black hole surrounded by an accretion disk, generating jets of material that punch through the star and produce a burst of gamma radiation detectable across billions of light years. The connection between Wolf-Rayet stars and gamma-ray bursts is not fully confirmed in every case, but it is well supported by theoretical models and by the statistical association between the two phenomena in the galaxies where they are observed. One Wolf-Rayet system that has drawn particular attention is WR104, sometimes called the Pinwheel Nebula. It is a binary system in which a Wolf-Rayet star and a companion star orbit one another, and the interaction between their stellar winds produces a spiral structure of dust that rotates on the orbital period of the binary. Observations have revealed this spiral with extraordinary clarity, making WR104 one of the most visually striking objects in the study of massive stars. It has also attracted attention because of the orientation of its rotation axis relative to Earth. If WR104 eventually produces a gamma-ray burst when the Wolf-Rayet star collapses, the direction of that burst depends on the geometry of the collapse. Some estimates have suggested that Earth lies within the potential cone of emission, though the distance of around 8,000 light-years and the uncertainties in the geometry mean that any risk is considered extremely low by researchers who study it. The broader population of Wolf-Rayet stars in the Milky Way numbers in the hundreds, and surveys continue to identify new examples, particularly in regions of the galaxy where dust obscures the view and earlier catalogues were incomplete. Each new discovery adds to the statistical understanding of how common these objects are, how they are distributed across the galaxy, and how their properties vary with mass and evolutionary state. That statistical picture feeds back into models of stellar populations and galactic chemical evolution, connecting the detailed study of individual extreme stars to the larger questions of how galaxies change over time. Chapter 7. SGR 1806-20. The Magnetar that reached Earth. Everything we have discussed so far has involved stars that are extreme in ways that are visible. Objects so large, so luminous, or so unstable that their behavior can be tracked across decades of observation, and their properties measured through careful analysis of the light they produce. The object we are going to consider now is different in kind. It is not large in the way that red supergiants are large. It is not luminous in the way that R136A1 is luminous. It is, in fact, extraordinarily small by stellar standards. A dense remnant roughly 20 kilometers across, smaller than many cities on Earth. What makes it one of the most closely monitored objects in the galaxy is not its size, but the intensity of what it produces, and the fact that on one occasion, what it produced reached Earth and left a measurable mark on our planet's atmosphere from a distance of 50,000 light-years. SGR 1806-20 is a magnetar. To understand what that means, it helps to begin with what it once was. Magnetars are the remnants of massive stars that have ended their lives in supernova explosions, leaving behind a collapsed core so dense that a tablespoon of its material would have a mass of more than 100 million tons. This collapsed core is a neutron star, an object in which the pressure of the collapse has forced protons and electrons together into neutrons, producing a sphere of nuclear density matter held up not by thermal pressure or electron degeneracy, but by the quantum mechanical resistance of neutrons to being compressed further. Most neutron stars are remarkable enough on their own terms. They pack more mass than the Sun into a sphere the size of a city, rotate at rates ranging from once every few seconds to hundreds of times per second, and produce powerful beams of radiation that sweep through space like lighthouse beams. But magnetars are neutron stars with magnetic fields that place them in a different category entirely. Where an ordinary neutron star has a magnetic field perhaps 1 trillion times stronger than Earth's, a magnetar's field reaches levels 1,000 times beyond that, approaching 1 quadrillion times the strength of Earth's magnetic field, a figure that has no meaningful analogy in everyday experience. The magnetic field of a magnetar is not merely an abstract record holder. It is the source of everything that makes these objects so extreme in their behavior. The field stores enormous amounts of energy, and when it shifts, when the crust of the neutron star, deformed by magnetic stresses, suddenly cracks and settles into a new configuration, that energy is released in an outburst of X-rays and gamma rays that can briefly outshine the entire galaxy. These events are called magnetar flares, and they are among the most energetic phenomena that occur in the universe on human observable timescales. SGR 1806-20 was identified as a source of soft gamma-ray repeater bursts, periodic outbursts of high-energy radiation, and monitored with increasing attention as the instruments capable of studying it improved. It sits roughly 50,000 light-years from Earth, near the center of the Milky Way, embedded in a region of dense gas and dust that makes optical observation difficult, but does not impede the X-ray and gamma-ray detectors on orbiting satellites. Chandra, the Rossi X-ray Timing Explorer, and several other space-based instruments had been tracking its periodic bursts for years when, on the 27th of December 2004, it produced something that went far beyond anything previously recorded from a magnetar. The event lasted approximately 0.2 of a second for its most intense phase, followed by a longer period of oscillating emission that continued for several minutes. In those fractions of a second, SGR 1806-20 released more energy than our Sun produces in approximately 250,000 years. The burst traveled outward in all directions at the speed of light, and when the leading edge of that pulse reached Earth, it encountered our planet's ionosphere, the layer of charged particles in the upper atmosphere that reflects radio waves and plays an important role in long-distance communication. The effect was measurable. The ionosphere, which normally transitions between its daytime and nighttime configurations in response to solar radiation, was pushed from its nighttime state to a configuration resembling its daytime state, on the side of Earth facing away from the Sun, in the middle of the local night. This was caused not by sunlight, but by gamma radiation from a star 50,000 light-years away. Several satellites detected the burst directly, and some had their instruments saturated by the intensity of the signal. Radio communications in certain frequency bands were briefly affected. The event was, by any measure, the most energetic thing to reach Earth from beyond the solar system in recorded human history. The fact that it caused measurable effects rather than catastrophic ones is entirely a consequence of distance. At 50,000 light-years, the energy that reached Earth was spread across an enormous sphere and represented a tiny fraction of what was emitted. Had SGR 1806-20 been within 10 light-years of Earth, well, within the neighborhood of nearby stars, the same event would have been capable of stripping away a significant portion of the ozone layer, with consequences for life on the surface that would have been severe and long-lasting. The researchers who study magnetars are careful to note that no known magnetar is close enough to pose this kind of threat, and the nearest confirmed example is several thousand light-years away. But the 2004 event demonstrated, in a way that no previous observation had, that these objects are capable of affecting environments across interstellar distances. The monitoring of SGR 1806-20 and other magnetars has intensified since that event. The question of what triggers a giant flare, whether it can be predicted from the smaller bursts that precede it, and whether the magnetic field configuration of a magnetar in an active state carries any warning of a major event, is one of the central problems in magnetar research. Progress has been made in understanding the smaller, more frequent bursts that these objects produce regularly, and statistical models of their activity have been developed and refined. But the giant flares, of which only a handful have been observed, remain difficult to predict and imperfectly understood in terms of the precise physical mechanism that releases their energy so suddenly and on such an extraordinary scale. What the sustained observation of SGR 1806-20 has contributed to is a broader understanding of the magnetar population and what these objects tell us about the endpoints of stellar evolution. The connection between magnetars and the fast radio bursts that have puzzled astronomers since their discovery has been strengthened by observations of a galactic magnetar producing a burst in the radio band, suggesting that at least some of the mysterious flashes of radio energy detected from distant galaxies may originate from objects like SGR 1806-20. Each piece of the picture adds to a portrait of an object class that was entirely unknown to science until the late 20th century, and has since become one of the most actively studied categories of stellar remnant in the galaxy. Chapter 8. Why these stars matter to science. We have now spent time with 6 objects that sit at the outer edges of what stars are physically able to be. A red supergiant close enough to Earth that its dimming was visible to the naked eye. A binary system that erupted with near supernova energy and survived. A star so expanded that light takes hours to travel around it. The most massive stellar object currently known, sitting in a satellite galaxy and burning at a rate that will exhaust it in a cosmically brief time. A class of stars that strips itself bare through the force of its own radiation. And a magnetar whose magnetic field released enough energy in a fraction of a second to alter the atmosphere of a planet 50,000 light-years away. Each of these objects is remarkable on its own terms. Together, they point towards something larger about why extreme stars occupy such a central place in modern astrophysics. The most immediate reason is that extreme stars are the universe's primary manufacturers of heavy elements. The hydrogen and helium that filled the early universe were produced in the first few minutes after the Big Bang, in a process called Big Bang nucleosynthesis. Everything heavier than that, the carbon in living cells, the oxygen in the atmosphere, the iron at the center of the Earth, the gold and platinum and uranium that occur in trace quantities across the planet's crust, was produced inside stars and distributed through space when those stars died. The more massive the star, the heavier the elements it is capable of producing, and the more violently it dies, the more thoroughly those elements are dispersed into the interstellar medium, where they can eventually be incorporated into new generations of stars and planets. A star like R136A1, burning through its fuel at a rate proportional to its enormous mass, is producing elements in its core that smaller stars never reach. The sequence of nuclear fusion reactions that proceeds through hydrogen to helium, then to carbon, oxygen, neon, magnesium, silicon, and eventually iron, runs to completion only in the most massive stars. The iron core that forms at the end of this sequence is what triggers the collapse that produces a supernova, and the supernova itself is responsible for producing many of the heaviest elements through processes that require the extreme conditions of a collapsing stellar core. Every atom of gold that has ever existed was produced in an event of this kind, and understanding how those events unfold requires understanding the stars that produce them. Wolf-Rayet stars contribute to this picture in a specific and important way. Because they shed their outer layers continuously throughout their lives, they enrich the surrounding interstellar medium with processed material long before their final explosion. The gas and dust around a Wolf-Rayet star carries the chemical signature of the nuclear reactions occurring in its interior, and studying that material gives astronomers a window into stellar nucleosynthesis that does not require waiting for the supernova. The shells and nebulae surrounding these stars are, in a sense, a slow preview of what the final explosion will eventually distribute more widely. Eta Carinae contributes something different. Its great eruption in the 1840s released energy at a level that approaches a supernova without being one, and understanding how that was possible matters for the broader question of how massive stars lose mass near the end of their lives. The models of stellar evolution that describe how a star moves from the main sequence through its final stages have historically been better at describing the early and middle portions of that journey than the final approach to collapse. The behavior of luminous blue variable stars like Eta Carinae, the episodes of extreme mass loss, the eruptions that scatter enormous quantities of material into the surrounding space, is one of the areas where observations and theory have been most difficult to reconcile. Each new piece of data from the ongoing monitoring of Eta Carinae is a constraint on those models, and better models mean better predictions of what other massive stars will do. Betelgeuse contributes in a different direction still. Because it is close enough that its surface can be partially resolved by the highest resolution instruments available, it offers something that most stars cannot: a direct view of the large-scale convective motions occurring in its outer layers. The surface of Betelgeuse is not smooth and uniform like the simplified stellar models of earlier decades assumed. It is covered in enormous convective cells, regions where hot material rises and cooler material sinks, on a scale that dwarfs anything in the Sun's convective zone. These structures are thought to play a role in the mass ejections like the one that produced the Great Dimming, and studying them in a star close enough to resolve provides data that can be applied to the broader population of red supergiants that are too distant to image directly. The Magnetar SG R1806-20 contributes to a different branch of physics entirely. The interior of a neutron star is one of the few places in the universe where matter exists at nuclear density in bulk quantities, and the physics of that state is not accessible to laboratory experiments on Earth. The behavior of magnetars, the way their crusts crack under magnetic stress, the way their fields evolve over time, the way they release energy in flares, provides observational constraints on the equation of state of nuclear density matter, which is one of the fundamental unsolved problems in physics. Every Magnetar observation is, in a sense, an experiment performed by the universe on conditions that no human laboratory could replicate. There is also a practical dimension to the study of these stars that is worth acknowledging. Betelgeuse will go supernova at some point, and when it does, The event will be visible across the observable universe and detectable by every instrument sensitive to the relevant wavelengths. The neutrino burst that precedes the visible explosion by hours will pass through the Earth and be detected by underground neutrino observatories before any telescope sees the brightening star. This sequence of events, from neutrino detection to optical brightening, to the development of the supernova remnant over years and decades, will be one of the most scientifically productive events in the history of astronomy. The preparation for it, the accumulation of baseline data about Betelgeuse's current state, the development of models that predict what the explosion and its aftermath will look like, is one of the reasons the monitoring of this particular star carries such long-term scientific value. The stars we have been exploring are not curiosities at the edge of the catalogue. They are, in various ways, windows into the processes that have shaped the universe as it currently exists. The nucleosynthesis that produced the elements, the mass loss that enriches the interstellar medium, the collapse events that produce the densest objects in nature, and the extreme physics that occurs in conditions no laboratory on Earth can approach. Watching them carefully is not merely an exercise in astronomical record-keeping. It is a way of reading the universe's own account of how it works. Chapter 9. What continuous monitoring has changed. There is a difference between knowing that a star exists and understanding what it does. The catalogues of stellar astronomy have been accumulating for centuries, and the number of stars that have been observed, named, and assigned a position in the sky runs into the billions. But knowing that an object is there, and having a measurement of its brightness and colour recorded on a particular night, is a very different thing from watching it across years and decades and building an understanding of how it behaves over time. The science that has emerged from the sustained monitoring of extreme stars is not simply a more detailed version of what catalogue astronomy could provide. It is qualitatively different, and in several cases, it has changed the direction of entire research programs. The most immediate thing that continuous monitoring has provided is the ability to detect change. This sounds obvious, but its implications run deep. A single observation of Betelgeuse in any given year would show a star of a certain brightness and colour. It would not reveal that the star is variable, that it pulses on a 420-day cycle, that it has a longer secondary variation layered beneath that, or that it is capable of a dimming event as dramatic as what occurred in 2019 and 2020. All of that information is encoded in the time series, the long sequence of observations taken repeatedly over years, and it is invisible in any single measurement. The same is true for Eta Carinae's 5.5-year orbital cycle, for the periodic X-ray variations that track the interaction of its two stellar winds, and for the gradual brightening that the system has shown over the past century as the dust ejected in the Great Eruption slowly thins and allows more of the star's light to reach us. Time series data has also allowed astronomers to distinguish between different kinds of variability and understand their physical origins. When Betelgeuse began dimming in late 2019, the fact that researchers had decades of prior brightness measurements meant they could immediately place the event in context. They knew what the normal pulsation cycles looked like and could identify that what was happening fell outside those patterns in specific ways. Without that baseline, the great dimming would have been much harder to interpret. The eventual explanation, overlapping pulsation trough and dust obscuration, depended on having enough historical data to know what normal looked like, and therefore to recognize the ways in which this event deviated from it. For Eta Carinae, the decades of monitoring have produced something even more structured. The 5.5-year orbital period of the binary means that each close approach of the two stars is an opportunity to test and refine the model of how their winds interact. The researchers who have been tracking the system through multiple periastron passages have watched the X-ray emission rise and fall in ways that are broadly consistent with their models and inconsistent with others. Each cycle adds another data point, another constraint, another opportunity to test whether the current best model is adequate or whether something in the observations requires revision. This iterative process, played out over decades, is how the current understanding of Eta Carinae has been assembled, and it would not have been possible without the commitment to sustained observation that began long before the current generation of researchers entered the field. The development of space-based astronomy has transformed what continuous monitoring can achieve. Before satellites, the range of wavelengths available to astronomers was limited to what the atmosphere permits: visible light, some infrared, and radio. The high-energy universe, the one that reveals itself in X-rays and gamma rays, was essentially invisible. The Magnetar SGR 1806-20 was not simply unstudied before the era of X-ray astronomy. It was undetectable. Its defining behavior, the bursts of high-energy radiation that make it scientifically important, does not produce any signal that ground-based telescopes can observe. The entire category of soft gamma-ray repeaters, of which SGR 1806-20 is the most studied example, only became accessible to science when instruments capable of detecting the relevant radiation were placed in orbit. This expansion of the observable spectrum has not been a one-time event, but an ongoing process. Each new generation of space telescope has opened new capabilities, and in many cases, those capabilities have revealed behavior in already monitored stars that earlier instruments could not have detected. The NuSTAR telescope, launched in 2012, operates at higher X-ray energies than Chandra and was able to detect the hard X-ray emission from Eta Carinae that pointed toward cosmic ray acceleration, a result that required both the new instrument and the existing archive of lower energy observations to interpret correctly. The James Webb Space Telescope has added infrared sensitivity that allows the dust around Betelgeuse and Eta Carinae to be studied in ways that were not previously possible. Each new instrument does not replace what came before, but layers on top of it, and the result is a progressively richer understanding built from multiple decades and multiple wavelengths of observation. Continuous monitoring has also produced unexpected results, findings that were not anticipated and that have opened new areas of research. The discovery that SGR 1806-20 and other magnetars may be connected to fast radio bursts is one example. Fast radio bursts were discovered in 2007 and spent more than a decade as one of the deepest mysteries in observational astronomy. Millisecond flashes of radio energy arriving from apparently random directions with no clear physical explanation. The detection in 2020 of a fast radio burst from a galactic magnetar, arriving simultaneously with an X-ray burst from the same object, was a result that depended on having instruments already pointed at that magnetar as part of its ongoing monitoring program. The connection between magnetars and fast radio bursts was not something that was predicted clearly in advance and then confirmed. It was found because the right instruments were running when the right event occurred. This element of preparedness, the value of having instruments already trained on an object when something unexpected happens, is one of the strongest arguments for sustained monitoring programs. Science often advances through planned experiments that test specific hypotheses, but some of the most important results in astronomy have come from events that were not predicted and could only be captured by instruments that happened to be watching at the right moment. The 2004 giant flare from SGR 1806-20 was not forecast. The great dimming of Betelgeuse was not anticipated in its specific form. The eruptions of Eta Carinae in the 19th century were observed by astronomers who had no theoretical framework to explain them. In each case, the value of the observation was enormous precisely because it revealed something that existing models had not predicted, and that revelation was only possible because someone was watching. Looking at the arc of what monitoring has produced, from the first systematic brightness records of variable stars in the 19th century to the multi-wavelength campaigns of the present day, what emerges is a picture of science advancing not through single decisive experiments, but through the patient accumulation of context. The understanding of Betelgeuse that exists today was not achieved in any single observation or any single decade. It was built up across generations of researchers, each contributing a piece to a picture that none of them could have assembled alone. The same is true for Eta Carinae, for the Magnetars, and for the Wolf-Rayet population. The science that results from this kind of work has a different character from the science of discovery. It is slower, more cumulative, more dependent on the willingness to return to the same object year after year without the guarantee of a dramatic result. But the understanding it produces is correspondingly deeper, and the surprises it occasionally delivers are all the more valuable for being grounded in such a thorough knowledge of what is normal. Chapter 10. What we still don't know. There is a particular kind of comfort in uncertainty, not the uncertainty that comes from ignorance, from having no tools, no data, no framework for asking questions, but the uncertainty that remains after decades of careful work, when the questions that persist are the ones that have survived every attempt to resolve them and have emerged sharper and more precisely defined in the process. The stars we have been exploring throughout this video are surrounded by that kind of uncertainty. What is not yet known about them is not a gap in the record that better instruments will simply fill. It is a set of genuinely hard problems that sit at the boundary of what current physics can explain, and the researchers working on them know it. The most immediate open question surrounding Betelgeuse is one that has no clean answer. When? The uncertainty in the supernova timing is not a failure of stellar models, but a reflection of how difficult it is to determine the internal state of a star from external observations alone. What can be measured is the surface, the brightness, the temperature, the velocity of the outer layers, the composition of the material being shed. What drives the eventual collapse is the state of the core, where the nuclear reactions are occurring and where the sequence of fuel exhaustion will ultimately reach its end. The core is hidden behind layers of stellar material that cannot be seen through directly, and inferring its state from surface observations requires models that are themselves uncertain. The 2019 dimming event and the apparent shift in Betelgeuse's pulsation cycle afterward have added new data to this picture, but they have not resolved the fundamental uncertainty about how close the star is to the end. There is also an open question about the mechanism behind the great dimming itself. The explanation that emerged from the observations, a surface mass ejection producing a dust cloud that obscured part of the star's light, is well supported by the available data, but the process that drove that ejection is not fully understood. What caused a convective plume large enough to eject a mass equivalent to several times that of the Moon to rise from the star's surface at that particular moment? The answer likely lies in the interaction between the star's convective motions and its pulsation cycle, but the details of that interaction are not yet captured in existing models with enough precision to explain the event from first principles. Understanding it better requires both improved observations of Betelgeuse's surface structure and theoretical work that pushes the models of red supergiant convection beyond their current limits. For Eta Carinae, the central mystery has persisted for nearly 2 centuries. What caused the great eruption of the 1840s remains one of the most debated questions in stellar astrophysics. The event released energy at a level that approached a supernova, ejected enough material to form a nebula that is still expanding and visible today, and left the binary system intact and continuing. No current model of stellar physics predicts this outcome cleanly. The leading hypotheses involve some combination of the binary interaction, the gravitational influence of the companion star disrupting the primary during a close approach, and instabilities in the primary star itself as it approached or exceeded the Eddington limit. But the details of how these factors combined to produce an eruption of exactly this scale, and why it happened when it did, rather than earlier or later in the system's history, are not settled. The possibility that Eta Carinae will erupt again is taken seriously by researchers who study it, and the monitoring programs are designed with that possibility in mind. What an eruption would look like, how much warning the existing data might provide, and whether the current generation of instruments would be able to capture the event in the detail needed to finally answer the question of mechanism. These are live considerations in the planning of observing campaigns. The system is known to be unstable in a fundamental sense, and the history of 2 major eruptions within 50 years suggests that the instability is not a one-time feature of its past, but a recurring characteristic of its present. The Wolf-Rayet stars carry their own set of unresolved questions. The connection between Wolf-Rayet stars and long gamma-ray bursts is theoretically motivated and observationally supported, but not definitively confirmed in the sense of having a direct observation of the collapse of a known Wolf-Rayet star, producing a gamma-ray burst. The challenge is one of timing and distance. Gamma-ray bursts are brief. The collapse events that produce them are not predictable, and the Wolf-Rayet stars close enough to study in detail are not necessarily the ones whose collapses will be observed from Earth. WR 104's potential alignment with Earth has attracted attention and some concern, but the uncertainties in both the geometry and the physics of the eventual collapse are large enough that confident predictions are not possible. What is clear is that the question will remain open until either a very nearby Wolf-Rayet star is observed to collapse, or the theoretical models reach a level of precision that removes the current ambiguities. For the Magnetars, the deepest open question concerns the interior physics of neutron stars, the equation of state of matter at nuclear density, which governs how these objects respond to the stresses placed on them, and what forms of behavior are possible at the extreme conditions they represent. The giant flare from SGR 1806-20 in 2004 released energy at a rate that stretched the existing models of how much energy a magnetar's field can store and release. Subsequent theoretical work has produced explanations, but the models are constrained primarily by the handful of giant flares that have been observed, and the statistics of such rare events are not yet sufficient to distinguish clearly between competing theoretical frameworks. Each new giant flare, if and when one occurs, will add a critical data point to this picture. The connection between magnetars and fast radio bursts, suggested strongly by the 2020 detection of a galactic burst, raises questions that are still being worked through. If magnetars are the primary source of fast radio bursts, what determines whether a given magnetar produces bursts detectable at extragalactic distances? Why do some magnetars show radio emission and others do not? What is the relationship between the X-ray activity that characterizes the known magnetar population and the radio bursts that fast radio burst surveys detect from distant galaxies? These questions have generated a substantial body of theoretical work and observational follow-up, and the field is moving quickly, but the answers are not yet in hand. There is something worth sitting with in the nature of these open questions. They are not simple gaps waiting to be filled by better data alone. They are places where the physics is genuinely hard, where the processes involved are complex enough that even with good observations, the interpretation requires models that push against the limits of what current theory can provide. The uncertainty around when Betelgeuse will explode is not going to be resolved by a single better measurement of its brightness. The mystery of Eta Carinae's great eruption is not going to be solved by one more orbital cycle of X-ray monitoring. These are problems that require both more data and better theory, and the interplay between them is where the science actually lives. What the monitoring programs provide in the face of this uncertainty is something quieter and perhaps more valuable than answers. They provide the accumulation of context, the slow building of a record detailed enough that when something unexpected happens, there is enough background to interpret it. Betelgeuse will eventually explode, and when it does, the decades of observations that preceded the event will be among the most scientifically valuable data in the history of astronomy. Eta Carinae may erupt again, and if it does, the instruments trained on it will capture something that was only partially observed the last time it happened, nearly 2 centuries ago. SGR 1806-20 may produce another giant flare, and the networks of satellites now monitoring it are better equipped to study that event than anything that existed in 2004. The watching continues not because the questions have been answered, but because the questions are worth asking. These stars are the universe working through processes that shaped everything around us. The elements in the ground, the light in the sky, the physics that governs the behavior of matter at its most extreme. Sitting with them, even at a distance of thousands of light years, even through the intermediary of data and models and instruments that translate their behavior into forms we can study, is a way of being present to something larger than any single life or any single generation of science. The record accumulates, the understanding deepens, and the stars go on doing what they have always done, indifferent to the watching, and entirely worth watching nonetheless. If this was a good companion tonight, a like or a subscribe helps other curious minds find their way here.